on Born-Haber cycle, which is an energy cycle that uses Hess's law to determine ionic lattice enthalpy. Here are two ionic lattices, sodium fluoride and magnesium oxide. You will recall from your bonding days that when an ionic bond forms between cations and anions, the cations and anions automatically arrange themselves in a very precise manner, which we call a crystal lattice or a lattice structure, where the cations are surrounded by anions and vice versa. Born-Haber cycle is interested in basically finding out how much energy is stored in these things. Now, it's not as simple as that, but we will take a closer look at it. Here, I have shown you two lattices. Before we move on, it's important for you to notice that lattices of ionic compounds have various amounts of energy. In this case, magnesium oxide has more energy than sodium fluoride. In other words, it has a higher lattice enthalpy or lattice energy than sodium fluoride. The reason for that is twofold. Number one, the distance between the ions is smaller, and number two, the charges of the ions is larger. If the charges are larger, that means that those two cations and anions will attract each other strongly, and if the distance is smaller, that also will lead to a stronger attraction and in turn a stronger ionic bond, which basically means that it's going to be harder to break the bond. We can see this here. This is Coulomb's law, and the force of attraction between two charges. We don't need to know this for chemistry, but that's just a good way of showing you this. The Q1 and the Q2 are the two charges on these, in this case, in the case of the ions, and the R squared would be the distance between them. Obviously, if your Q1 and Q2 are larger, that means your numerator is larger. That's going to give you a bigger force of attraction. And if your radius is smaller, that's also going to give you a stronger force of attraction. Lattice enthalpy is described as how much energy is needed to take 1 mole of an ionic solid and convert it into its gaseous ions. In this case, we have a sodium chloride lattice, and I'm converting it into gaseous ions. As you can imagine, this process is endothermic, and here's the amount of energy that's required. We can show this with an equation, and this is typically how we show the equation for lattice enthalpy. And the enthalpy change that is associated with this would be labeled lattice enthalpy. This value right here is already there, and that's what Born-Haber cycle is interested in. Now, lattice enthalpy can also be thought of as gaseous ions coming together to form a solid, in this case, solid lattice. So if I were to do this, this is also labeled lattice enthalpy. The only difference is the first one here is actually endothermic because you are going from a solid to these gaseous ions. And the second one, when you take gaseous ions and they combine to form 1 mole of the solid sodium chloride, in this case, this is going to be exothermic. So this will obviously have a positive value, which is listed there, and then this will have a negative value. The only, obviously, the one thing here that you have to keep in mind is that the value, the magnitude of the lattice enthalpy will be the same for both of them. It just depends on which way you're looking at this. All right. How do we find lattice enthalpy? Now, lattice enthalpy is very difficult to determine directly because of the number of ions in a lattice. So we use Hess's law of heat summation. Now, if you recall, Hess's law of heat summation basically states that if I'm interested in finding the enthalpy change for a reaction, in this case, A to D, and for whatever reason I can't do that directly, perhaps because the reaction is too slow or the reaction is too explosive and I can't find the enthalpy change experimentally, if I can break that reaction down into simpler steps for which I can find enthalpy changes, or I can find other reactions that I can manipulate mathematically to get my overall reaction, then this holds true. Which means that the sum of the enthalpy changes of those simpler reactions will equal the enthalpy change for my target equation. Now, this is only true if these arrows, you can see these arrows here, follow nicely, or if all of these equations add up to give you your overall equation. In this case, you can see I can't go from A to D directly, but I can go from A to B, B to C, and then C to D. Now, this is what we call an energy cycle, and that's what the Born-Haber cycle is. So keep in mind here that in order for this to be true, these reactions must add up to give you the overall reaction or equation. So you can see very quickly here that if I write A goes to B, the first one, B goes to C, and then C goes to D. If I were to add these, obviously I'm canceling the like terms, just like math, just like we did in Hess's law, you will end up with A goes to D, which is my target equation. This must be the case in order for this to be true. Now, if one of these arrows was pointing the other way, so let's say, for example, it was A to B and then B to C was pointing the opposite way. Remember, these arrows, in order for us to create a cycle, these arrows all must be pointing in one direction nicely. What I would have to do is I would have to flip this equation right here and flip that arrow. So this would be C to B, and then I can continue. All right. So let's see if we can create a Born-Haber cycle for sodium chloride. So here's the equation for the lattice enthalpy of sodium chloride. Remember, you can think of lattice enthalpy as gaseous ions forming a solid lattice or a solid lattice forming gaseous ions. The value will be the same, the sign will be different. This is labeled as lattice enthalpy. This is what I'm interested in. Now, like I said, this is my target equation here. For whatever reason, I can't find this. Well, this is because there's way too many ions in that lattice. So this is the same situation. This is what I'm looking for, but I can't find the enthalpy change directly. So in this case, we had delta H1, we had first reaction, second one, and third one. Here, we are actually going to come up with those simpler reactions, and then we can see if we can add the enthalpy changes for all of them to determine the lattice enthalpy. So where do we start? Well, we try to break this process into simpler steps. So let's focus on the sodium ion for a second. Sodium ion in nature is found as solid sodium. We all know that. Well, what are the processes that are involved in taking solid sodium and making it into a gaseous ion? Well, first of all, I'm going to have to convert that, change the state. So I'm going to have to change the solid sodium into gaseous. And then that gaseous then has to be converted into a gaseous ion. In this case, there are two processes involved. Now, both of these processes are simple enough for us to measure the enthalpy changes for. This one here is labeled as delta H of atomization. And this process, as you can imagine, you're going from solid to gas, requires energy. So this is actually endothermic. So this will have a positive value. The value for this is actually listed in tables in your data booklets. The next one is sodium going to sodium plus. Well, you will recall from grade 11, this is ionization energy. In other words, for me to convert sodium into sodium ion, I'm going to have to take one electron away from it. This is labeled as enthalpy change of ionization energy. Now, you could put first ionization energy here, but sodium only loses one electron, so I'm just going to leave ionization energy. Keep in mind, if this was calcium, calcium becomes calcium 2 plus, which means that calcium will have to lose 2 electrons. And there, you would have to have two values, first ionization energy and second ionization energy of calcium. For now, we're just focusing on sodium chloride, and we will leave it as that for now. And this one also is endothermic, because we all remember to take an electron away from of a neutral atom, neutral gaseous atom, you have to put energy in. All right, let's now focus on the chlorine. Chlorine in nature is found as Cl2 gas. Well, I'm going to have to convert the Cl2 into Cl gas, and then the Cl into Cl minus. Well, again, for me to, in this here, there are two processes involved. Now, this one here is labeled as enthalpy of atomization as well. Or sometimes it's called enthalpy of bond dissociation, because you are breaking the bond between the two chlorines. And this one here, you are giving chlorine an electron. Here we were taking an electron away. Here we're giving it an electron. When you give a neutral gaseous atom an electron, we call that electron affinity. So this is enthalpy of electron affinity. All right, we are now getting close to creating a full cycle. So in order for me to make this a full cycle, I just need to create one more connection, and that one more connection is this, the solid sodium plus the chlorine here, creating solid sodium chloride. This is solid, by the way. Now, this one here is labeled as enthalpy of formation. Now, you guys will recall from our previous studies on energetics that enthalpy of formation is the enthalpy change associated with forming 1 mole of a compound from its elements in their standard state. And that equation is always balanced for 1 mole of that compound. That's why typically when you're looking at Born-Haber cycles, for a diatomic element, in this case, like sodium chloride, there will be half in front of it. And essentially that half is there to balance that equation. Also, when you are now ready to find the lattice enthalpy, you will see that this half actually plays a role here. Let's take a look at now how we can calculate lattice enthalpy. What I have created here is a Born-Haber cycle. Essentially, I have created this cycle right here. The only problem is, in my case, my arrows are not all pointing nicely in one direction. So if you take a look at this one here, the arrows are all going nicely in this direction, so I can go from A to B. My arrows are actually not going directly into this. I know this one is going there, but I want to create a cycle just like I did there. So here's what I'm going to do. In order for me to calculate the lattice enthalpy here and create that energy cycle, I am going to flip that arrow backwards. Now, anytime you flip an equation in energetics, we change the value of the enthalpy change. Whatever the enthalpy change for sodium chloride is, we are going to change that. I believe it's around negative 411 kilojoules per mole. That's going upwards. We are going to be changing the sign of that because I have now flipped this arrow. Now you can see by flipping that arrow, I have actually now created a cycle. All these arrows are actually nicely pointing in one direction. I've created the cycle. That's called the Born-Haber cycle. So now, once I've created the cycle, once I flip this one here, how do I actually determine the lattice enthalpy? How do I calculate the value of it? Well, keep in mind that all of these enthalpy values here are actually listed in your data booklet. All 5 of these are listed there. Enthalpy of atomization, first ionization energy, electron affinity, atomization of chlorine, enthalpy of formation of sodium chloride. They were all listed in your data booklet. So here now is the formula to calculate lattice enthalpy. It's not a formula. All I'm doing is this concept right here. I'm going to say, okay, my lattice enthalpy now is the sum of all of the other ones. It is going to be the enthalpy of atomization of sodium plus the enthalpy of ionization energy of sodium plus the enthalpy of electron affinity, delta H of electron affinity. Sorry, let me just write that here a little bit better. Plus, now here's the thing that you need to be mindful of. The bond dissociation value of chlorine is given to you in that table. Because you're using half of it, you're only using 1 chlorine in this process here, you are going to have to multiply that by half. So it'll be half times the delta H of atomization of chlorine. That's got to be, it's important for you to remember that. And then plus, remember, we are flipping this delta H. So plus is going to be minus the enthalpy of formation. I ran out of room here, so let me do that over here. So it's going to be plus minus the enthalpy of formation. And the reason I'm putting a minus here is because I am flipping that. Remember, we flipped this arrow here so that we could create that cycle. Now, once you have all of this, all you have to do is just plug the numbers in, and then you will get your lattice enthalpy. Here are the enthalpy changes that I was telling you about. So we have enthalpy of formation of sodium chloride in that case, in our case, atomization. We had electron affinity, we had first ionization energy, and then we had lattice enthalpy. Lastly, we're going to take a look at an energy diagram from our Born-Haber cycle. This is basically the same Born-Haber cycle that I drew. It just looks slightly different because it is showing you this whole process happening on an energy graph or diagram. So this is energy here. Now, you can see here that arrows are pointing up and arrows are pointing down. Any arrow that's pointing downwards, that is indicating an exothermic process, and all the arrows that are pointing upwards indicates an endothermic process. Here, you can see here, solid sodium chloride going into gaseous ions. That is lattice enthalpy. Remember, that's the endothermic version of it. This is what I'm interested in. I'm interested in finding the value of that large gray arrow. So if we take a look at this now, this is actually pretty much the same as what I drew, except, like I said, for the energies. So if you take a look at sodium here, here's solid sodium going into gaseous sodium, and gaseous sodium and going into gaseous ion. The enthalpy changes are labeled. This will be atomization because you're going from solid sodium to gaseous sodium, and then to go from gaseous to gaseous ion, that's labeled as first ionization energy, and here are the values. And then we are going from chlorine into a single chlorine gas. So single chlorine atom. And here, this is also labeled as enthalpy of atomization, and here's the value for chlorine. Next, if we continue, you can see here now the chlorine becomes chloride. And here is electron affinity. Notice that the arrow is pointing downwards, which means that this process is now exothermic. Here's the enthalpy change for that. And lastly, the enthalpy change for enthalpy of formation of sodium chloride. Let me clean this up a little bit. For the formation of sodium chloride here is negative as well. So if I just look at these arrows visually, all I want to do is I want to find the size of this arrow. Well, if I flip this one upwards, now I have all of these arrows pointing in that one direction. I can find the sum of all of these arrows and then just take that away from it. Now, I'm not taking it away. I'm adding a negative number. So obviously, I'll be taking that away from it, and that'll give me the size of this one. So if I wanted to use this energy diagram right here to calculate the enthalpy change or lattice enthalpy for my reaction for this process right here, or for sodium chloride, it would be this enthalpy change plus this one, plus this one, plus this one, obviously, and then this would have to be flipped. So this would become a positive value because I'm changing the value of that. So once you do all of that, so it'll be 411, which is this guy, plus 108, which is this one, plus 498, which is this one, plus 121, which is that one, obviously, and then minus 351 or plus negative 351, it doesn't matter. When you add all of those up, that's going to give you the lattice enthalpy.